morning. So, as we take it from the last talk I had, today what I am going to do will be called multi-site host guest interactions. Multi-site host guest say complexation, interaction or complexation. In other words, how the host gas complexation is formed, there is a thermodynamic approach to it. So, let me first draw. So, this is my guest and I draw a host also for that. Okay. So, this is host and this as I told you earlier that host has information coded and guest recognizes that to make host guest complex. So, the simple complexation we can write host plus guest forms a host guest complex, and equilibrium constant for this would be, say I will write like this, will be K gives by H G upon G, right. So, now from this K we get that minus delta G equals RT ln K, RT ln K. So, from this you can get all these things. Now, there are problems while dealing with that. So, let me write, there is a multi-site I have written, multi-site host guest, and that is what makes this host guest complex and this. So, I will write here is say A1, let me write D1, then I will write D2. So, these are the information A2, then A3, then say D3, and it will interact with something like I am writing this interaction to signify interaction. This is close to D2 A1. So, it will interact both ways. So, all kinds of interactions are possible, okay. And then maybe D4. So, it will keep on going. There are actually thousands of these AD interactions possible. So, consequently, the total binding energy constant In this case, this is total binding energy constant, but if I look at it very carefully, the total binding energy constant will be kT, equals say K11, K12, K22, okay, K23, etc. All right. So, it is the multiplication of individual interactions, and this is a multi-site, though they are like that, it goes on. So, how we express K11? We can express K11 as follows. R say 1 D1 R prime, and then R A1 R prime D1. So, I am putting all this is R and this is R prime. That is how this R and R prime comes. Followed? So, similarly, say K I j, I can write K I j equals R A I D j R prime, all right, upon R A I R prime D j. Generally, we can write. So, now look at very carefully. The total constant, okay, this is expressed in, what is the unit dimension, I can say, it is expressed in per mole, kT, this is kT. So, kT is expressed in per mole, and each individual K11, K12, K22 are also expressed in per mole. So, therefore, on the right side of this equation, on the right side of this particular equation will be m to the power n, and on the left side is m to the power 1. So, that is a problem. In an equation, if you have different dimensions on the left and right, you cannot equate them. So, there is a major problem, all right. So, therefore, what we can write? We have to go dimensionless, okay. Let me show you. Okay, I had earlier. Okay, 4, 5. Okay, let me go. So, we can go dimensionless. How can you go dimensionless? Suppose we are discussing this host and guest, each are interacting in 1 molar solution. All right, host is a compound, guest is a compound. They are dissolved in 1 molar solutions, and they are allowed to react. So, therefore, the molar fractions, if you say molar fractions, what will be the molar fractions? Molar fractions will be, I have to divide 1 upon 55.6, okay. molar concentration, I have to divide by 1 upon 55.6, it becomes molar fraction. That means, what I am saying is R AI, okay. So, what I will write concentration in molar fractions, it will be 1 upon 55.6. When I do like that, okay, when I do like that, then it is becoming dimensionless. It is becoming dimensionless, and there is no problem on the left side and the right side. So, therefore, I can write now, instead of the usual concentration that we write, we will express concentrations as ratio of molar fractions. So, I can write K I j, okay, this is per mole, is equal to, let me write R AI d j R prime, just same thing I am writing as earlier. So, R AI d j R prime, and if I express is equivalent to, I can write right now. You have to practice at home this one, okay. So, we can write R AI d j R prime upon 55.6 upon. So, this molar concentration and divided by this 55.6. Okay. Then R AI divided by 55.6 R prime d j by 55.6, and from here it was mole inverse. So, that also to divide it by this, it will come here divided by 1 upon 55.6. Okay. So, that means I can multiply it here 1 upon 55.6. I have taken it down to this side. Okay. All right. So, this is now my expression. This is now my expression that it is dimensionless, and both left side and right side will have same, no problem with dimension, and we can simplify it by saying this is my chi. It is not ideal chi, but still R A I d j R prime one upon 55.6 divided by Okay. So, I just simplified this whole thing and put this upon this as chi. So, chi and this extra comes 55.6, and all of you know how I am putting 55.6. For example, in water, okay, that is the solvent of choice normally. So, in water you have 1 liter of water or 1000 ml has 1000 grams, and molecular weight of water is 18. So, you divide by that, it comes to 55.55, it goes on. So, I write 55, okay. You can write 55.56, that is how the, or say 55.6, I have written 55.6, that is also good enough. Okay. So, 55.6. Okay. So, therefore, I can write is equal to K I j chi upon 55.6. So, now K I j x is now a dimensionless quantity. So, I expressed K I j in mole inverse to K I j chi in molar fractions when I divide it by 55.6. All right. So, therefore, I will next I will do this. So, I had done chi I j equal to 55.6 into K I j. K I j is in mole inverse. Okay. So, K T means total. Okay. Total. It will become K11 chi K1 say K12 chi K22 chi and so on and so forth. Okay. Or I can also write 55.6 to the power n, then I can write K11, K12, K22, you keep on writing. Okay. All right. So, I can write that, but we know that KTX equals 55.6 KT KT. Therefore, you solve everything, it comes out to be, you must do it at home to make sure what I am writing is correct, to the power n minus 1, from where minus 1 comes, that you have to convince yourself. When you put all these equations, then it will come be all right. K11, K12, K22, etc. So, this equation we have derived assuming complete additivity, and that is correct. Okay? That is complete additivity, we are having complete additivity of these interactions, and it is a dimensionless quantity. So, we can get the K T value from individual pairwise interaction. This is called pairwise interactions. Pairwise interaction. Okay. So, these pairwise interactions, from these pairwise interactions, there are many pairwise, say hundreds, and from hundreds we can get the kT simply by multiplying it with 55.6 into to the power 99. Okay. So, this meaning another thing I told you the before earlier also couple of times, that these intermolecular forces, okay, that is responsible for this multi-site in the pairwise interactions, they are very small in quantity. However, the total is 55.6 because there are hundreds or there are many. So, therefore, since there are so many interactions, so to the power, so 55.6 to the power that number n, suppose n is 100 I told you, then it becomes 55.6 to the power 99, that is a huge number. So, therefore, total kT becomes substantial. Okay. So, that is the basic principles of this host and guest. Host and guest, when they combine over a large surface of area. There are n number of interactions possible, they are called pairwise, and this multi-site pairwise interactions, and if there are 100 such, I assume 100 such, there are thousands of such. So, 100 there, then what will be the result? We find individual pairwise interactions and multiply that with 55.6 to the power 9. So, that is a huge number, and when you calculate everything, kT becomes substantial. So, once we know kT, we can know delta G T chi, delta G equal to minus RT ln kT. Okay. So, we can know from the kT value, we can know this delta G value, all right. From kT value, we can know this delta G value. So, delta G will be substantially negative, even though individual pairwise interaction is very small. Now, when I say that pairwise interaction, I have to say you something. Pairwise interaction, let me write pairwise interaction. How to go about it? Okay, suppose one, as I said that the other day, suppose this is host, I am just writing a host, and there is a host and there is a corresponding guest, followed corresponding guest, which will form, let me write guest also. This guest, this is host, this is guest, and it was the total. So, we make a molecule which may not have this top part. In other words, what I am saying, I make a host, this host. You compare this host with this host. Suppose I say H and this is H1. Okay. So, in this H1 you can say this part is missing, this part is missing, right. So, your guest also will be similarly missing something. That means, I can know interaction between, or I can make this host with this guest. Say I can do this way also, I can tell you. Suppose, yeah. So, I can make this compound and this compound. In other words, I can make this compound and I can make this compound. Then therefore, this interaction, suppose interaction between these two. So, these two interactions I can determine. How interaction you determine? You can determine interactions from NMR relaxation, and from NMR there are many well defined equations are there, and in these all these equations Professor Hans Jörg Schneider, my good friend, he has papers in so he has given how from NMR interactions you can know these pairwise interactions. So, it is a long term process. I have written a very big and given only one. So, similarly, there are, this host is not so small, this host is very big. So, corresponding guest is also big. So, I make this particular small compound, then I make this particular small compound, okay, and correspondingly guest. So, each time I find out the pairwise interactions, and from this pairwise interaction I am assuming they are additive in nature, and because of that I can get the total interactions, pairwise interactions of the host and the guest, so that the entire Kt values or this host guest complex entire this I can determine the Kt values, because I can know individual K11, K12 from pairwise. So, you can understand that this is not a one day or 1 month projects, this requires years. Okay. So, this is a very, but then you can ask why you want to do that if it becomes years. Well, we want to do that because to probe sometimes, all right. So, sometimes we have to do that, K11 separately, K12 separately, K22, K23 like that, assuming they are completely additive. Then we can find out Kt, we can find out Kt. Once we find out Kt, then you can find out all these things, all right. So, now we have said earlier also that, so what is a molecular recognition? I will again say that molecular recognition is the readout of information coded in the host by the guest molecule. And remember, as I told you earlier also, I will re-emphasize it that host and guest, we are interested to find out that when host and guest form a complex, host guest complex, then the complex must have a property very different from either host or guest. Then it is a very useful one, because ultimately from supramolecular compound that I am forming, I should get a property out of that which is useful to us. So, that must be kept in mind. I have not talked about entropy. Now, entropy, what will happen when these two systems combine, there is a change in entropy, but in this case, so that is why it is only an approximate. It is not an absolutely correct way to do that, but because of entropy is less, much less in significance compared to the delta H values and all that. So, therefore, delta G we can get fairly accurately, or we can know that okay, we are in this ballpark. All right. Now, from now on, that these few introductory lectures, now I will come to the main point, that is known as supramolecular synthon from next lectures. Thank you.